Okay. Well, welcome everyone to HMRI's scientific seminar series. We're delighted that we're moving away from Zoom and doing this now as a hybrid situation. So I'm really delighted to introduce our guest speaker today, Dr. Alfredo Sadun. I've known Dr. Sadun for many years. Our paths have crossed several times especially on looking at therapies for mitochondria. And he's one of the best lecturers in town. So I think you're in for a real treat this afternoon. Just as a little bit of background, Dr. Sadun holds the Flora Thornton Endowed Chair and serves as the chief at Doheny and vice chair of ophthalmology at UCLA. He graduated from MIT in 1972 and went on to earn both his Ph.D. and M.D. from the Albert Einstein College of Medicine. Following his residency in ophthalmology at Harvard Medical School and a fellowship in neuro-ophthalmology, he joined the full-time faculty at Harvard's Department of Ophthalmology in 1983. In 2014, Dr. Sadun played a key role in guiding Doheny's transition to UCLA. Dr. Sadun has distinguished himself across really all three pillars of academic medicine, and that includes research, education, and of course, clinical care. His groundbreaking research and vision earned him the Lighthouse International's Lifetime Achievement Award in 1999, Pisart Award. For his dedication to education, he received the 2002 Straatsma Prize, the highest honor for residency teaching from the AAO and AUPO. He has won several other major prestigious awards throughout his career. An internationally recognized authority in neuro-ophthalmology and diseases of the optic nerve, Dr. Sadun has published more than 410 peer-reviewed articles, 80 book chapters, and co-authored or edited 5 books. His work has been cited over 30,000 times, and he holds an H-index above 75. He also led national efforts in ophthalmology education, becoming the inaugural president of the AUPO Program Directors Council. Dr. Sadun continues to direct an active laboratory focused on clinical, psychophysical, and laboratory investigations of optic nerve diseases. He was the first to identify an optic neuropathy associated with Alzheimer's disease. In 1993, the United Nations appointed him to lead an investigative team studying an epidemic of optic neuropathy in Cuba. Across his career, his research has illuminated the critical role of mitochondria in the brain, optic nerve, and retina. And with that, I'm going to turn this over to Dr. Sadun, who's going to discuss how Castro got us to quantum mechanics and the formation of reactive oxygen species. A very interesting title for your talk. Dr. Sadun.
Thank you. Can you hear me with this portable mic? I guess so. Yeah. So thank you, Bob. As Bob says, we've been fortunate to have had a personal as well as professional relationship for many years. I've also enjoyed my relationship with HMRI, which is I realized as I was ruminating about it at coffee today, much longer than you might think. In fact, much longer than anyone else in this room. I was trying to decide between pursuing my MD side or my PhD side, as the training had led me to this test. And I could have done an internship or I could have done a postdoc. I got a postdoc at Caltech lined up. And then there was this very interesting man that says, I got an answer for you. And his name was Richard Bing. And this was in 1978. And he proposed that I work out of HMRI to do my Caltech postdoc and to continue being an intern in medicine at Huntington Hospital at the same time. Intellectually very gratifying, but my wife says I was chronically exhausted and never was able to remember anything we ever did on a weekend. But it was a small price to pay for what was really a fun and professionally important year. But anyway, so I have gratitude to this institution and to the people who have formed it. As Bob noted, it's a pretty weird title. Let's see if I can justify it. We're going to be talking about all the items on that list, even including the quantum mechanics. But the essence of this talk is going to be about reactive oxygen species, something that I'm sure interests every biological scientist and the people in this room. No financial conflicts. Now, the subject of this talk came about when I received something called the Jacobson Prize, something our society gives once a year to somebody for their lifetime of research. What it really is, of course, is proof that I'm old. These awards always come about when you're old, and people wonder how much longer you're going to be around to receive these awards. But it was a challenge because they asked me to give a talk about my lifetime of research. And I'd like to think that my lifetime of research can't be squeezed into a talk. But it led to something interesting, which is the title that you just heard. And so I will try to do something along those lines. My story for this purpose will begin in 1993 with the trip that Bob alluded to Cuba. Every year we had our scientific meetings in Sarasota, Florida, called ARVO. And because I've been doing this already for some 10 or 15 years, people knew where I stayed and how to find me. So I wasn't surprised when somebody showed up who was the head of something called Project Orbis, which was a missionary group that went around the world. And he said, listen, there's this epidemic of blindness just down the beach in Cuba, and everybody there is going blind. How many is everybody? I said, well, tens of thousands of people. And they think that it has to do with work that you've done research in. And so I said, I'll think about it. And he said, no, you're right near it. We need to get you on a plane and fly you down to Cuba. I have connections, and I can get the State Department to charter a flight for you. While I was thinking about it, I was approached by a second group an hour or two later while I was playing with my kids on the beach, and that was the World Health Organization. It's part of the UN. And they said the same thing. They said, you've been identified as somebody who might be able to help with the epidemic. Well, why are they looking for Americans? I thought they hated us. I said, well, they do, but you keep coming up as somebody whose papers relate. And more importantly, from the point of view of the State Department that should object to this, they don't want this virus that they are convinced that it's causing the blindness to jump the 90 miles to the US. And so it's in their interest that you go down there. Well, I wasn't going to fly directly there as they had suggested, but I was going to go back to Los Angeles and do these 4 things it says here. One is make a series of calls checking with the State Department to make sure that they really wanted me to go and they would support me, and they did. 2 is I would put together a team. I wasn't going to go alone. 3, I was going to research what things it could be. I needed to spend some time. Now, back then there was no Google. So if you're going to do research, you're going to spend it in the library. And I did, in fact, close myself up at the USC library for a couple of days. And 3 is I was going to check with my wife, Deborah. As it turned out, 1, 2, and 3 were easier than I thought. Deborah called the State Department herself, and they said, I overheard part of the conversation, this woman said, well, if it was my husband, I wouldn't let him go. We're at a state of war with Cuba. We have no responsibility. If he gets in trouble, don't call us because there's nothing we can do. But most of all, it's a virus, all our scientists have agreed, very contagious, and he's going to come back blind. But I got to go. So in fact, I got to go on 5 different occasions, but I'm going to confine my comments today to this first trip in May of 1993. I also was given a team of 8 members from the UN called PAHO, Pan American Health Organization, but I'm going to emphasize my nuclear team that I brought with me. That's the core of discovery here. Jim Martone, who was the head of Project Orbis, and not only a good clinician, but thank God was used to international politics because he bailed me out on many occasions where I would have caused problems. And Lily, who was my laboratory technician, I'm sorry, my clinical technician, who knew how I like to do my examinations. When I went back to LA and I talked with the State Department, I said, I need you to help me out by giving me, excuse me, I'm going to bring this chair out front because I have a back issue. And if I put my foot up on the chair once in a while, it'll help me out. I said, I need you to give me as much background information as you can, of course. The next morning after I got back to LA, a plainclothes guy shows up actually I showed up at my office at 7, he was there waiting for me. And he gives me a package which was wrapped in butcher block paper and with a twine across it that had this written on it. Wow, I thought, this is cool, just like in the movies. Not exactly, as you'll see. And I said to him, you know, I don't have a security clearance. And he goes like, so okay, fine. So what do I do now? He says, you go in your office, you close the door, because that's what this means. And I leave, goodbye, and he heads out. So I did, opened it up, and all this top secret stuff was newspaper clippings, or actually Xerox copies of newspaper clippings. Apparently the world knew what was going on, just not the US, which had a news blackout from Cuba. The most useful of these was the Spanish newspapers, And for every one of them, there was a typed up transcript made by the State Department so I could read it in English. And Australia. I don't know why, but Australia was on top of this and had a series of articles about this epidemic. From those articles, all of them, I sat down and within about 6 hours had put together at least this, which is a description of how many cases there were for each quarter of each year. So the epidemic started at the beginning of '92. We were now in the early or middle part of '93, and these numbers are exploding in terms of each quarter being a bigger number than before. So there was about 50,000 cases at my review. This, by the way, is only half of this quarter because it was still early. So we organized to go back to Miami to catch this charter flight that the State Department was going to provide. And on the flight back, I was with Lily, and this movie showed. You may remember it, A Few Good Men. It's good for me to give you some context, because Jack Nicholson plays a general from Guantanamo Bay who's reminding everybody who has forgotten about Cuba, and he says, we are in a state of war with this country. And he has this line where he says, I have breakfast every morning in Guantanamo Bay, looking out, where I know there are at least 300 yards away are 1,000 Cuban soldiers who would just as soon see me dead. And mistake on my part, I whispered to Lily, and we'll be having breakfast with those soldiers. But clearly I shouldn't have been doing that. Among other things, it turns out she was Puerto Rican, but that her husband, by the way, Lily was about 23 and had a 6-month-old newborn. Her husband was of Cuban extraction, and he agreed to let her go or to support her in this as long as his parents didn't find out, because they would have gone nuts because the Cubans in Miami were pretty upset with Castro. So anyway, this probably wasn't wise for me to put her on such alert. And to give you more context, the Cuban Revolution was in 1959. That's when Castro took over. Within a couple of years, he got really pissed off at and by the U.S. So the U.S. put a total embargo on everything. The Russians provided everything that Cuba needed, including missiles, but we won't get into that part of the story. And in '92, pulled out, which meant that the economy of Cuba was destroyed, and all the oil that they had been getting from Russia, that basically had a bargain that said, you give us sugar, we'll give you oil, fell through. So now Cuba had plenty of sugar, but no oil, and so there was nothing running on that island. I mean, no cars, no tractors, there were horses dragging the plows, and so they were starving. And there wasn't much way of importing food because of the embargo, so they were in big trouble. The other historical context is that about 15 years before this, Castro didn't like the way the economy of Cuba looked. It was based on selling cigars and selling rum. So he emphasized something that he called biomedicine. Biomedicine was going to start with vaccines. He said, you know, the U.S. makes fine vaccines, but they're too expensive. The third world needs vaccines. We will provide it for them at a tremendously lower cost. He didn't say, but I think he recognized that maybe the quality control wouldn't be quite as good, but you know, even a less effective vaccine will save lives. And the concentration of the intellectual part of Cuba was going to be on virology and molecular biology. So in a communist country, you don't pick your field, it's picked for you. And the best and the brightest people in that country were all virologists. That's an important context. After we arrived, in fact, the same day that we arrived, we get put up in a place that I'll call a hotel, although it wasn't. It was a special guest house for people invited by the government to visit. And Lily and I then walked across the street to this big fancy building, which is their biotechnology building, which is mostly about the virology, and went where there was a reception for me. And I had asked to be debriefed by their scientists and had expected to attend that. But what I didn't expect was to encounter this man. That's Fidel Castro. Now, you guys will probably recognize him, but you won't recognize me because I look so much younger. So Fidel Castro is the center of attention, of course, and that's until Lily walked in, and then she became the center of attention because Castro immediately started to hit on her. She was attractive. You'll see pictures of that. And she was in a predicament. On the one hand, she was a married woman who didn't want to get involved with a dictator of a country, especially when she had to go back to her in-laws. And on the other hand, she didn't want to piss him off and undermine my work. I thought she handled it brilliantly. But I noticed every time that I would leave them alone, I'd come back, she would have had her 8 pictures of her granddaughter whipped out of her wallet to show them and remind them of her status. He did hit her with one line, not in my presence, but she related it to me later. He said, you know, how does it feel to be the most powerful woman in all of Cuba? Because I'm the most powerful man and I'll do anything for you. So then for 5 hours, the generals did their debriefing and explained what they had found. This was one of the most important things, so I was able to get them to give me the slide. Color-coded view of the concentrations of people who had gone blind in different parts of the island. The pertinent element here is that the highest concentration was here, this western area called Pinar del Rio. I'll tell you two things of interest. Number one is when there was a dengue outbreak about 4 years earlier than this, it began here, and according to the Cubans, I doubt that it's true, but the Cubans say some American frogmen went here and started the dengue outbreak, and the same place that this is starting. Number two is that this is the sugarcane area, and that's where they used to ship sugarcane to Russia, but no longer. And as you see, the concentrations go from this color to purple to green to orange and finally to yellow. It's a progression from west to east. And the only place in the island that there was no blindness was, it's underneath this thing that says recorded, but there's an arrow right here pointing to Guantanamo Bay that had no cases of blindness. Interpretation by the general was, it's a virus, probably planted by the US, although they didn't have any direct evidence yet, spreading from west to east at a rate of a wavefront of 26 kilometers a day. You might want to remember that number, but that was the average of all these increments, this gradient. So that was a strong evidence, they said, for a viral cause. But there were many other elements as well. For 5 hours, in a room about this size, Castro and I were up at the dais. There was a third person who was translating into my ear. It was all held in Spanish. And the various people were giving reports. One, for example, was that they used nasal electrophoresis of interferons. Remember, they're all virologists. And the guy said it was 80% successful. And I thought it was interesting that Castro shot up and said, not 80%, 78%, you're exaggerating. Which may have meant many things. Number one, Castro was paying attention. Number two, he sat through all 5 hours. Number three, that he knew his numbers. And number four, if he didn't know his numbers, they weren't going to contradict him anyway. But the most important thing Castro said during those 5 hours was when I asked him questions. And I was perturbed because they kept on talking about the virus being grown out of the CSF. 121 out of 126 CSF samples grew out virus, Coxsackie virus to be precise. And this was their final proof. And I kept saying, was there a leukocytosis? That is, were there white blood cells? They're talking about a meningitis. The CSF should have been filled with white blood cells, and they wouldn't talk about it. Were they lymphocytes or were they neutrophils? I wanted to know that, and they weren't answering. Finally, Castro gets up and says, you're bullshitting, Sadun. Don't do that anymore. Answer his questions or we're never going to get anywhere. There were no white blood cells in the CSF, which meant there was no infection. I should have added one other thing. At this point, I was totally convinced there was no infection. I was pretty convinced anyway from what I already had been able to research and read. But I asked a couple more questions that they were forced to answer. How many cases did they see in the orphanages? None. How many cases did they see in the army barracks? Very, very few, much less than the rest of the countryside. Any sort of infectious disease likes to rip through the very young and the very old. The retirement holds, nothing, and very crowded, the soldiers in the barracks. So this didn't have any characteristics of being a viral infection. So every day we went to examine patients, and the first thing that this slide is to remind me to mention to you is that Castro was a genius. He was amazing. He asked me, because of course there were spies everywhere, what were these glasses that I was using, that none of the ophthalmologists in their country had anything like them. And I explained it was something I had actually patented myself. They're cross-polarizing filters, 2 of them per lens, so that if they're in parallel, light goes through. If they're perpendicular, you block all light. You crank them down to where the 2 eyes see light equally bright, and you can therefore use that to calculate the ratio of ganglion cells in the eyes, one side to the other. And then he said, what's this? And he whipped out a piece of paper that was stored next to them, and it had a little nomogram that said this many degrees of rotation corresponds to this percentage of brightness sense diminution by the Polaroid lenses. And I said, it's a very complicated nonlinear relationship. He says, of course it is. It's cosine squared theta. Now, I knew it was cosine squared theta, not because I figured it out, but because when I published the papers, I had to figure it out. And I have a system. Both of my brothers are mathematicians, a subject that I'm going to get back to at the end of this lecture. And I always would write to them, and if their answers were the same, I figured it was true. And they said cosine squared theta. So he says, you don't understand why? And I said, I don't. He takes out a napkin and he derives it from basic trigonometry why it has to be cosine squared theta. This was on the fly. So I was just very amazed. So he saw how impressed I was, and that just encouraged him even more. So he would regularly show off his intelligence, and he liked me because I was just smart enough to realize he was smarter. And it was an impressive display all along. Here he's looking at the Krebs cycle, because I'm already figuring out that this has something to do with that and the mitochondria. And I'm showing him the Krebs cycle. This is also a chance for me to show you the other players. This is my lab technician, Lily. She actually spent all day long in a t-shirt and jeans helping me with the patients. But since he would always compliment her on her appearance, when we got back, it always changed to get her dressed up. This is the Minister of Health. I'm sorry, this is the Minister of Health. This is the head of the National Foundation, Academy of Sciences for Cuba. This is Jim Martone, the person I told you about who kept bailing me out politically. And we're going over the Krebs cycle, and Castro is saying, why do you keep making references to here? Don't you know it? I said, no, I don't. I thought all American MDs had to know the Krebs cycle before they take their boards. Yes, they do. They all memorize it, and then the day after the boards, they forget it. And he said, that's a terrible habit. Test me on that from now on. And every day he'd say, well, go ahead, test me on the Krebs cycle. I memorized it, and I still remember it. He did. He wasted his efforts on such silly stuff. This is a typical patient, a 35-year-old sugarcane worker who had noticed over a period of a couple months a 30-pound weight loss. Of course, it was in kilos, and it wasn't even that. It was belt notches that we used a World Health Organization converter for. And then in 1 week, he lost his vision in both eyes. And he got down to 2400, which is well into legal blindness in both eyes. And the back of his eye looked like this. Now, they had characterized this sort of right, the Cubans, as optic atrophy. That is to say, this half of the disc was pale compared to this half, you see. But missing the more subtle and important point, which is that this half is not pale. Missing even more subtle points, which is that the nerve fiber layer, which spread out like spokes coming from the hub of a wheel, are very well seen here and here, but they're missing from here to here. And that's the same size as has the atrophy. So clearly, this is an injury that is not only specific to the optic nerve, but to this subset of fibers from here to here, which is the temporal area. I was calling this the temporal wedge. Later publications actually refer to that as Sadun's wedge, which was pathognomonic for the disease. So it's very helpful to have a sign that you could objectively find in these patients. And not all the patients had it, because some of them were, in fact, malingering, because if they had the disease or if they were hysterical, they got special treatment. They got into hospitals, they got better food. And remember, everybody's starving. They're all losing weight. Here are a couple more examples of the backs of the eyes. And in every case, you see the same pattern. You see half of the nerve is pale and thickened fibers there and there, but no fibers on the pale side. No fibers on the pale side. There was always this temporal wedge. Now, I knew, and it helped my thinking, that those fibers are distinguished in two ways. One, there's many more of them, and two is they're very, very small. Now, why they're small is a subject for another time, but the smallest fibers are going to have interesting surface area to volume ratio relationships that play a role in understanding the pathophysiology of this disease, and would have no relationship to viruses. After a week of work, we thought we had made some important progress, so we had a chance to make a presentation. There were about 1,000 people working in something called the National Operative Group, MDs and PhDs equally, and they attended this big presentation of mine, during which we explained what we had found and what we thought were good definitions for the disease. It was actually on the issue of definition of the disease that we got a lot of pushback. People saying, I know my patients have it, and I have a patient who you would say doesn't have it, and I'm right and you're wrong. And how dare you, after 1 week, come in and say this after we've been working on it for a year. And I would explain to them false positives, false negatives. At one point, I asked for a flip chart, and I drew out Venn diagrams to try to understand that I'm not telling them that they're wrong. I'm just saying we need to have a pure collection of patients to do proper epidemiology on. This went on for probably about 3 hours, until finally Castro got up and said, then it's settled, we'll use Sadun's way. It was far from settled, of course. It was not my influence at all on them that made any difference, but my influence on him. At the same time, Lily was working at her job, which was to dilate and photograph. Those beautiful photographs you saw were all taken by her on the fly. And while waiting for the drops to work, per our plan, she would get the same history that I had gotten and then compare it with what I had gotten in Spanish, because she was Puerto Rican. And she had known that one of the most important questions that I wanted to ask was, were there any family contacts? Did you have it? Did your father have it? Did your mother have it? Did your kids have it? And so on. And she finally hit one where a brother said, yes, my sister has it. And the sister said, my brother has it. Great. Then she knew the issue is to find what commonalities there were. Do you live together? No. Do you eat together? No. Do you party together? Everything they could find, she could think of, the answer was no. But when do you see your sister? Every other Sunday. Oh, do you go to Mass together? No. What do you do together? We take a walk in the park. Fortunately, Lily, being bright, said, this sounds a little bit bizarre. What did it really mean? And after some proper discussion, she found out that on every other Sunday, they would go to a place that they could buy bootleg rum. They bought the rum that had not been aged fully. Now, don't get the wrong impression. I'm not talking about wood alcohol, which is improperly made alcohol. That causes formic acidosis, and among other things, take a little too much of that and it'll kill you. Nobody died from this epidemic from this issue. What we're talking about is rum that's not aged. Now, what I didn't understand at this time is the importance of aging. Why every society around the world with its hard liquor ages it. And it's not just to improve the flavor. In fact, I suspect that the flavor improves because people have associated it with not having headaches. But if you drink unaged rum or unaged anything, you'll get a headache because there'll be trace amounts of methanol, because that's what bacteria make, about 1 part in 100. But because ethanol has a lower vapor pressure, it sticks around for a while. The methanol with a higher vapor pressure evaporates, and with aging, you change that ratio. But anyway, she didn't know all this. She just knew that these people were doing that, and that was very interesting to us. So at this point, I was expecting the flight the next morning. So we had talked to Castro about how we were leaving and took a photograph of us together, you'll see in a second. But he said, what do you mean? You're not finished. You haven't figured out exactly what's going on, much less the solution. And so I said, yeah, well, we'll come back when it works out, but we have a flight tomorrow. And he says, you know, the name of the airport is the Marti Airport. It's not. It's my airport. And it's going to be closed tomorrow, so you can't fly out. So he did it with a twinkle in his eye, I got to say. And like leadership we see today sometimes, purposely a game is played between joking and telling the truth in order to intimidate. And it worked. I was completely intimidated. I think the color must have washed out at me when I realized I was not in control anymore. He must have felt badly for me because he whispered to some people. And 10 minutes later, a telephone appears. Now, in those days, there was no cell phone, so it had a 50-foot tail of cord that went to another room. But he picks up the phone and he starts to chat. And I finally understand from context, he's chatting with my wife. He's chatting with Deborah. And he's saying things like, don't worry, he's fine, he's healthy, I'll let you talk with him in just a minute, ask him anything you like. And then he passes the phone to me. And I repeat that I'm fine and healthy. And that I'm to tell her, according to Castro, that I'm going to be coming back a week late, that she should call the hospital, explain circumstances, cancel my surgeries, et cetera, which she did. So we spent another week, which was a worthwhile week, because that's actually when we pursued the issue of Lily's contacts, had a better chance to talk with them and test them. Anyway, that's that final picture that we were supposed to take before I realized that Castro was just setting me up to spend another week. You notice that next to Castro is always Lily. So the biology is, we had concluded after that week especially, that there were two hits that coincided together. The first was a depletion of folic acid. And when I said this to the group, it was denied, because they'd actually done a study comparing the folic acid of husbands and wives, and the husbands usually were the ones going blind, but not the wives, and they discovered that they were about the same levels of folic acid, but there were low levels of folic acid, because there was a second hit to discriminate between them. Anyway, the second hit was from the trace amounts of methanol that was in their rum. Now, methanol becomes formate, and formate gets detoxified by the body if it's not too much. But what detoxifies formate? Folic acid, which they didn't have. So the small amounts of formate accumulations were not enough to poison the brain and cause edema and all the terrible things that that can cause. But it was enough to poison one particular thing, which is the mitochondria. Formate blocks oxidative phosphorylation, and the mitochondria were not working well. Now, I had a hunch that was true because of that particular appearance of the temporal wedge, which is exactly what I see in a disease we're going to talk about in a few minutes called Leber's hereditary optic neuropathy. So the phenotypic expression, turns out to have been the same. So then we finally had a chance to come back to the US and analyze the 2 bottles of rum that Castro had given me, which were super aged and really wonderful bottles, and they ended up having essentially no methanol. And then I sent in 2 bottles that I was not able to get, but I was able to complain about not being able to get to the New York Times, and a Canadian ophthalmologist who deserves a lot of credit for this flew down the next day to Cuba, because he could from Canada, got me these 2 bottles and sent them to me, and when we sent them to the same labs, they came back 1% methanol, which is pretty close to the calculation that we had come up with. So on the basis of this, Castro said, what can we do? And I made a bad joke. He had been making jokes all along. And I said, I come from a capitalist country. If we want people to stop buying something, we just sell it for less. You can make your rum less expensive and stop the problem. And he said, boy, that sounds expensive. But of course, the real answer was to give folic acid. So they divided the areas of this epidemic into 3 parts of the island. They gave folic acid to each of the 3 parts, and the new cases dropped off to 0. So it worked. I went back on a second trip. This is the last slide I'm going to show, that second trip in September, just to compare. And the visual acuities that were 2400 were 2050, which was a lot better than I expected, because I had predicted there'd be no improvement in vision, because the atrophy means dead axons. Castro had said to me, they're getting much better. I think you've cured them. And I was saying, that's impossible. Let me see. The truth was somewhere in between. But for example, the color vision had gone from 1 out of 8 places to 7 out of 8. The optic atrophy had gotten, if anything, worse, but that swelling of the nerve fibers above and below that we saw before had gone away. And so that's how the disease sort of normalized, though not completely. But from that, I was able to get a number of NIH grants, making a mouse model of this disease that has led to some understanding of mitochondria. We would take the mice and we would take their folic acid levels down to the same levels as the human samples that we had brought back. We would titrate methanol to get to the same levels of formate as the human samples that we had brought back. And these mice, I'm sorry, they weren't mice, they were rats. These rats went blind. And the nerve fiber layer would swell in the same pattern, and they would have these tiny little vacuoles that we saw on in the human case, because I also got 1 case of a human that had died from a traffic accident, a horse traffic accident. The optic atrophy was replicated. And in the rat model, we were able to see that those little vacuoles, this is EM on the mouse that you can't do on humans, were actually mitochondria that had blown up. So the theory of this being a mitochondrial disease sort of came together. Now that started my interest in Leber's hereditary optic neuropathy, which is a genetic mitochondrial disease, one that Bob has already alluded to. So you can get a lot of mitochondrial diseases. I'm not going to go through all this long list, but genetically you can get it either because the mitochondria have got an alteration, or the nucleus has a DNA alteration that affects mitochondria, and that both exist. But I'm going to concentrate on talking about Leber's. And the key point moving forward I want you to keep in mind is that having the mutation is necessary but not sufficient for blindness. Many people with mutation are just fine 20/20 all the time. If you get a second hit, now in this case it's not folic acid and methanol, but it's a 2-hit story again. If you get a second hit, you go blind. And there's nothing in between. That's what's interesting. Nobody gets 20/40 or 20/80 vision from Leber's. You go from perfectly normal vision to legally blind vision, which speaks to there being some sort of reiterative process where once you get to the tipping point, a lot of things crash. The clinical manifestations of Leber's were the same as my Cuban patients, which is why we did this new shift in study. Bilateral symmetrical vision loss with loss of color vision, central field defects. And why? Because the papillomacular bundle, that's that temporal wedge of fibers, are for your center vision. And a temporal pallor of the optic disc, at least initially. So they looked, one genetic, one acquired, almost identical. I'll give you a typical presentation of what Leber's looks like. This is a young man who I've gotten to be close friends with. He went to San Diego in college with everything being perfect. He was on an athletic scholarship. Everybody that he knew about in his family was in good health, and he got involved in the fraternity lifestyle. And like most of my patients who crash and burn with Leber's, he started to smoke and drink because he was in a fraternity. And around November, noticed some vision loss, which is about the right lag time. His nerves looked bad, so they said, you have optic neuritis and probably MS, but the workup was negative. They said he had brain tumor and the workup was negative, et cetera, et cetera. Eventually he lost vision of the second eye, and the symmetry was apparent. And that's when he was referred to us, and the diagnosis was easy. He went blind between November and December My Brazilian patients with this, we'll talk about that shortly, all go blind in April, and both for good reasons. The biology is that the defect, the mutation, causes a decrease in complex 1 activity, makes less ATP and more ROS. When you smoke and drink, you might add to your environmental source of ROS, reactive oxygen species. And the optic nerve is the canary in the coal mine. ROS and mutations go to every cell in your body except the red blood cells. But for reasons we're going to get into in a second, the optic nerve is particularly vulnerable. And more than the optic nerve, the papullomacular bundle is the most vulnerable. This is because there's no myelin in the fibers that come out of that. If there were, they would lose transparency and you couldn't see. Myelin is not only good for faster conduction, but it provides for a great economy. The discharge of the axon occurs not along the entire membrane, but just once in a while, and that's the only area the energy has to be re-injected. This is an optic nerve from one of my Labor's patients in cross-section. And you see no brown here because there are no axons here. They're only in that little cluster. And at higher power, you realize there are these fascicles. Each one, by the way, carries 1,200 axons. And there are 1,000 of those. And that's how you get to the total of 1.2 million axons in an optic nerve. And that's where the fibers are still intact. The rest of it's gone. That's a particularly bad case. Usually it's just the temporal side that's involved. And the idea here is that you have reactive oxygen species change the mitochondria in a way electrically that opens up this pore called the MPTP, and that causes apoptosis, and that's suicide. The cell is killing itself because it's getting a message to do so. And its message is based on reactive oxygen species being misinterpreted, not as an accident of nature, but as a signal from the immune system that says, you must be a cancer because we don't like you. Here's the ROS. Kill yourself. The mitochondria normally accumulate in high numbers in the nerve fiber layer of the eye because there's no myelin. And when there is myelin, they only accumulate between the myelin, which is where the work gets done. Which brings me to Brazil. So we had another adventure, not Cuba, but Brazil, where we discovered a pedigree of patients who had this mutation. We found 362 members in the pedigree, which is pretty good because the previously largest number in the pedigree published was 26. So with this, we figured we could finally understand this disease better. It occurred in 8 generations, beginning with 1861, where somebody with the disease, a woman, because it's only carried by the female line, emigrated from Italy. And there's these 3 small cities about 100 miles apart in very rural Brazil, and all the members of the family had stayed there because poverty kept them from traveling. Carrier means you've got the mutation. Affected means you're blind. You remember, only a subset of them go blind. And we went every year for 20 straight years, bringing a bunch of volunteers to examine these patients to try to understand the disease. And a lot of what's in the textbooks now about the disease comes from those studies. And what we know is that complex 1 doesn't work, so the electrons don't get passed down the system, but make ROS instead. And if you take out this particular part out of the equation, 5 ATPs don't get produced, only 4, which, by the way, is not so much. So it's surprising that such a small decrease in production of ATP has such profound consequences. So we were able to create a model of this in mice. This is with Doug Wallace at Children's Hospital in Philadelphia. And the essence of the story is that he spent 23 years giving chemo and radiation to the mice until he got the mutation he wanted. It's a lot of work for a little gain, but it wasn't such a little gain. When he looked in there, to his surprise, the amount of ATP production was unchanged. The amount of mitochondria were increased by 20% to compensate for the 20% decrease in efficiency. Easy. But the ROS production was way up, and there was no complex 1 activity. The mutation was still complete in its effects. So that gave us some understanding. This was published in PNAS, which is sort of neat because the end paper I'm going to show you is also PNAS, which comes up with the answer to the questions this one raised. Why the tissue specificity? Because the optic nerve is vulnerable, and especially the papullomacular bundle is vulnerable. And why is that? Because of their size. These are the fibers that leave the optic nerve being separated out by position. And this is a technique called OCT. Bob knows that because we're doing OCT on Alzheimer's patients here. And what it turns out to be is that the place that has the smallest fibers, which is the temporal area, is also the place that they first swell and first die. Although if the disease progresses bit by bit, the other ones get involved. This was work from my colleague who came to Brazil every year for 20 years to do it. Starts there, inferior temporal portion of the optic nerve, ends there, superior nasal. So we took a number of optic nerves to do a more precise study. These were one of the 21 patients who had died with the disease that we got their optic nerves to do histology on. And I picked 4 as selected examples of mild disease, moderate disease, severe disease, and super severe disease. And you can see that there's a small bite taken off on the left. In every case, the eye has been oriented so the left is temporal. A bigger bite, a big bite, and all but a little piece left over, depending on the severity of the disease, but always as temporal progressing towards nasal, which makes perfect sense if you put a simple algebraic model to this, which says that the stress of the cell, which I call X here, is the number of nodes of Ranvier, that's where all the work is being done, times the length of the nodes, times the circumference of the axon at the node, because that's how much membrane is out there, and that's divided by the number of mitochondria providing the ATP. And so this turns out to be length times 2 pi r. This turns out to be length times pi r squared. Cancel out the parts, it's 2 over r. What does that mean? That means bigger is better. If your r is reflects a very small axon, you have a huge stress on the system. So this explains why you get that temporal wedge. So we did this particular measurement in a normal optic nerve, which took an enormous amount of work from one of my poor postdocs. He had to do EMs and count and measure all the axons of an optic nerve, and then create histograms for every region of the optic nerve. And he showed that in this region, inferior temporally, they're mostly small. In this region, supranasally, they shift the curve to the right. And then, of course, when we published, we said, well, we should show the photograph of this. And it sort of frustrated him because this photograph from here shows small axons. This photograph from here shows a lot of large axons. So it's evident to the eye without the statistics, but it's still better to do it quantitatively with statistics, I assured him. Then, in order to make it easier for us to understand, we made a grayscale chart. White is small, black is large axons, and this is the way a normal optic nerve has its distribution of axons by size. This was the patient with moderate labors, and the intact axons are these. And I hope you'll see immediately to the eye that this corresponds to dark here. Large is saving the situation. So we've understood some of these elements. I'm going to concentrate on my final comments on why did it happen all of a sudden? Degenerations like Alzheimer's occur over many decades, but this occurs over a couple of weeks. So we took these same measurements from my postdoc, and we fed them into a supercomputer, did Monte Carlo simulations. And if you created a simulation as this slide just did on the nasal side, this is the supranasal corner that gets spared, it burns through it a little bit, and then it stops because the reactive oxygen species kill the small axons. There are no small axons near them to pass it on, and the system burns out. There are large axons here which absorb the ROS but don't die. But over here, by the way, the concentration of small axons and the ratio is much higher for small axons. What's going to happen when we do the simulation there? Remember, this is on a normal, not a Leber's patient. It burns, and it burns, and it burns, and the wildfire goes on forever. Not forever, actually. It gets to the large axons, and then it finally burns out. And I hope you'll be impressed by how well this simulation on a normal optic nerve shapes itself, even to this little tongue here, to fit what really happens in nature on this case of Leber's on that side. So we think everybody believes our model now of that propagation of ROS as the issue. Okay, so it's a chain reaction, and ROS are the neutrons in this atomic bomb. But why do we have ROS in this disease? What has it got to do with electron movement? This was something that fascinated me because these are where the electrons get transferred in an earlier part of complex 1. These are iron-sulfur chains, and they're all pretty close to each other. In fact, they're almost always just under 13 angstroms apart, which struck me as pretty interesting because a paper had come out saying that photosynthesis has the same thing in their iron clusters. And the reason for this apposition is because quantum electron tunneling was occurring instead of regular physics. And so I thought, I wonder if what's happened, here's my theory, complex 1 looks so similar to photosynthesis that maybe nature does what it always liked to do, which is repurposes something. It just flipped it upside down, And now it can create ATP instead of creating carbon chains like photosynthesis does by going the other direction. I was wrong. Turns out, now we know more, it's the exact opposite. First came complex 1, and it was used to gobble up organic material back in the days that sulfur was the electron donor. When water became the electron donor, which is what happens in photosynthesis, it went the other way around. So photosynthesis came probably a few 100 million years after complex 1. But quantum electron tunneling, what is that? Ordinarily, an electron is held in place by certain electrical fields. And it goes to the field, bangs against it, and bounces back, unless it has a lot of thermal energy. If it has sufficient thermal energy, it hops over the barrier and reacts with something. That's the chemistry you learned in school. In quantum electron tunneling, you have an electrical wave of probability of position, and there's only a probability of it. It averages there, but it could be there, it could be there. And if it gets to a barrier at just the right distance on the other side for a reaction, it tunnels underneath and reacts away without ever having to go over the barrier, which is much more energy efficient. You don't have to put in activation energy. So my original idea was, let's go to complex 1 and test all this at absolute zero or near it, because this stops working when there's no thermal energy. No reactions occur at absolute zero. This would continue to work even at absolute zero. Cool experiment, but totally impractical. But fortunately for me, I said my brother was a mathematician. Long story as to how it happened, but he agreed to do this very hard work. And he started with Heisenberg's uncertainty principle, Schrodinger's equations, taking all the math out, and calculated the distances, and 13 angstroms was the key distance, just as we had hoped. So with that, I was able to go to the physics and chemistry department at UCLA, and they were impressed by that, and they said, okay, we'll do the study. So we did an in silico set of experiments, published it again in PNAS, and I'm very proud of this paper because I'm the only MD on the paper. I got to work with real scientists. And it says that this particular chemical which transfers electrons called CoQ10 is trapped in the mitochondrial complex 1, and that's the cause of Leber's hereditary optic neuropathy. But more particularly, what happens is that the mutation causes a A to G substitution, which means that instead of getting an alanine, you get a threonine at this particular position. That carries an OH group, and that OH interferes with the movement of coenzyme Q10. Here's what the whole complex 1 looks like. There's about 48, I think, proteins in complex 1, but I'm interested in this one protein called ND1. It forms a tunnel, and coenzyme Q10 slips in the tunnel, grabs an electron, slips out, actually grabs 2 electrons, slips out and delivers it to another molecule. But here's the tunnel, by the way. This is ND1, this purple thing, and now you've got this little nubbin sticking out of OH, and it interferes with the movement of coenzyme Q10. And the amount of energy required for it to get past there is 50 kT, which is absurdly high. So we figure instead of this molecule living for just a few nanoseconds there, it would take about 10 years for it to finally, on its own, escape. And that's obviously not going to happen. So it's complete constipation of coenzyme Q10. But that's not the worst of it. The worst of it is its position changes too. The OH not only blocks it from escaping, but shoves it in closer, even closer to where it gets the electron. Here's an example of the coenzyme Q10 molecule slipping through the tunnel, and this is where it picks up the 2 electrons from the iron sulfate chain. It's too close now. Because it's too close, something rather extraordinary happens. The math says that the quantum electron tunneling reverses direction. Instead of the electron pouring out of the chain into CoQ10, it goes right back up the chain. And as it comes out the other end, it has no choice but to become a reactive oxygen species. That's where they come from. So back to my model, you end up with a block in complex 1 that generates ROS. You add to it environmental factors that generate more ROS, changes the electrical potential of the mitochondria, releases cytochrome C from the cell, killing the cell by apoptosis. That's the signal for it to commit suicide. And that's how it happens, mostly in small axons that are unmyelinated. So when we submitted this paper, we were nominated for something called the Cosarelli Prize. And that's something the National Academy of Sciences gives to the best paper in the country. This one was nominated for biology. I didn't get it. Didn't happen. But what did happen is that a physicist wrote an editorial saying it was a cool paper, and he generated this cartoon. It's a pretty good cartoon. It shows the electrons accumulating because of the blockage. It can't drain out through the mutation, and therefore they spill out and become ROS. But I can't publish somebody else's picture, so I had my own version. And this is what my postdoc came up with just last week for this talk, and I like it. Okay, I like tea. I always have tea. So normally tea comes out through the spout, and you get your ATP. But in this condition, the coenzyme Q10 gets jammed in there because of that mutation. And worse yet, quantum electron tunneling forces the tea to come out and spill out over the top edge in the form of ROS. This is calculated and measured to be a 20% decrease, but this is calculated and measured to be a 200% increase. And now you've got a generation of a signal, and this signal tells the cell some funny things. Now, I think this is important because what we found out from Cuba, what was encouraged by Castro, and what we now know for LHON, might be a model for a lot of diseases, from macular degeneration to glaucoma to just aging. We're being approached by a lot of people in aging. And as Bob knows, because he's interested in aging and Alzheimer's, those diseases, and maybe Parkinson's too, are all alterations of mitochondria. These are just a small number of the many important people who've helped. Most importantly, I think Doug Wallace, who should have gotten the Nobel Prize for this in 1988, was the first to discover that you can have mutations in mitochondrial DNA, and his work continues to be amazing. This is a group that I bring down to Brazil every year, who give up their vacation time to work in a very sweltering circumstances, and it's pretty good group. We really enjoy working together. And this finally is my picture of the idea of bad signals. I don't know how many of you remember the myth of Theseus. Theseus was the son of the king, Aegeus, who decided that the pattern every year of having the Cretians come to steal away 7 maidens and 7 of the young men to take away to feed to the Minotaur was enough. He didn't want it to happen. So he, even though there was a lottery to pick out who had to go and die, he cheated and got himself on board the ship to go and do that. But of course he did it in order to fight, not to die. And when he was in Crete, he managed to kill the Minotaur, win the love of Ariadne, and the plan, which he had told his father, is to come back. And his father said, but you know, how will I know that you succeeded? And he said, simple. The ship of the Cretians has a black sail. I'll have to take one of their ships, but I'll substitute the black sail for a white sail. When you see the white sail come, you'll know I made it. But he and Adriana were partying too hard. I'll put it that way. If you read the original, it's more entertaining. And so in his drunken and erotic state, he forgot to switch sails. So my wife and I were in Greece, and I always insist on visiting things that are a little bit off the beaten path but have either philosophical or mythical significance. This is the spot of Aegeus' palace, from which he committed suicide when he saw right where that boat is, a black sail coming in. But it was mistaken. It should have been a white sail, and his son had successfully killed the Minotaur. And so here's a picture to show that false signals can cause a lot of trouble. And so it is with the ROS as an aberrant signal. My kids, of course, are all adults now. But every time I see this picture, I'm also reminded that my wife was not standing near the edge. She was behind me screaming, get him away from the edge. I think that's the conclusion of my talk. Thank you very much for your attention. Do we have time, Bob?
Great talk. Yeah, let's open this up to questions. And I want to start by asking, is there a role for reactive oxygen therapies such as superoxide dismutase, catalase, vitamin E, and any of these? I mean, have any of these ROS therapies have been shown to have any benefit in any of these diseases?
That's a great question. You know the answer, and it's important to discuss this. The work that we did and the work of hundreds of other people have pointed to the role of ROS as being really bad messengers. You have to be careful not to overly suppress them because they provide good functions too, because they are messengers. But still, we thought that using antioxidants was the answer, and it has not proven to be true. There's a guy, Sinclair at Harvard, who's made a company and a fortune by selling the message that blocking these ROS is going to save everybody from aging. It's been a failure. So I can give you some thoughts as to why it doesn't work, which is that there's feedback systems that are measuring the ROS production, and if the antioxidants start to work, they're reversed because you so depend on ROS. As an example, mitochondrial biogenesis, the production of new mitochondria, is based on ROS. So if the system says something's wrong here, the ROS are being overly suppressed, it's going to block that process. But whether that's the answer or there are multiple answers, there's certainly a lot of feedback loops here. It's not simple. And it's disappointing how little reactive oxygen species mitigation has worked.
The same is true in cardiovascular medicine. So there was a period of time, about 20 years ago, where there was a lot of excitement about oxygen radical scavengers and trying to reduce the size of heart attacks with these. And there was some experimental evidence, but it never really panned out, nor has it panned out for the treatment of atherosclerosis. Let's open this up to questions.
Hi, thank you. I have a medical question. Actually, I was just curious, as the people were losing their vision, what did they notice?
I'll give you the story of the one man that actually showed up there. He says, one day he came to the field and he was going to do the sugarcane cutting. And he said to his friend who used to come up on the other side of the hill, "Why did your wife use bleach? Your red shirt looks orange. It looks really silly." The guy says, "My red shirt's still red." So the color saturation was the very first thing they noticed. And then complete loss of color. And then about a week later, he said, "I can't see your head. You come up over the hill and you're headless. There's a big black splotch where your head should be." And this is the smallest fibers of the papillary bundle going first. They subserve the ability to see red. Slightly larger fibers until all the fibers from that area are gone and you get a central field defect. Interestingly enough, in this and the other disease, Leber's, the way I describe it to the patient's family, because the patient knows exactly what they feel, is he's going around, if it's a mild case, with a black baseball in front of his vision. If it's a medium case, with a black basketball. If it's a bad case, it's a giant beach ball right in front of his face, a black. But out of the edges, you can still see.
May I ask another question? New topic. Patients who have muscular dystrophies also have problems with the electron chain. Do they, and I went to medical school in the last century. I do know they had vision changes. I just wonder what their vision, what they report.
Not these vision changes. Their optic nerves are just fine. Actually, depending upon the muscular dystrophy, some of them have cataract formation. They have these famous things called Christmas tree cataracts, which are just very particular anatomical feature not seen anywhere else. But your point perhaps speaks to the fact that when you have accumulation of ROS from mitochondrial dysfunction, slight variations in the theme give very different phenotypes. In general, you end up with central nervous system is very much involved. I think it's because it's the most energy expensive organ in our body. You get cardiac problems, and you get smooth muscle more than striate muscle problems. And then you can get kidney problems. So all these are different versions of sort of the same disease.
Thank you.
Thank you for this very beautiful story. One question is mitochondria. Organs that are rich in mitochondria are heart and kidney. So I would expect to see a patient not going blind, but going more with heart issues and kidneys issue before the eyes. Can you explain why the eyes are targeted before
Sure.
the heart and the kidney?
Obviously, the last two questions are connected. You do see, as an example, Menge. Menge is a mitochondrial disease where the smooth muscle of the gut is involved, and you stop having peristalsis. You have cardiac problems. You can have long peripheral nerve problems. But in general, the area that I just said is the most expensive area to maintain is the brain. We're sitting here pretty quietly, and your brain, on average, weighs 2% of your body weight, but it's consuming 20% of the oxygen in this room right now. Why is the brain so expensive, more so than the kidneys? And the answer is every time you have an action potential, and of course you know you can have this action potential firing many times a second. Every time you have an action potential, you have to substitute the gradient of potassium and sodium. And every time you do a sodium-potassium exchange, that's 1 ATP. That's a huge consummation of energy, which is why evolution gave us an answer. And the answer is myelin. Myelin that we learned is only to speed up conduction, reduces the load on the brain probably about 1,000-fold. We could never have a brain our size if it wasn't for myelin, because it'd be so energy expensive. But anyway, that's the answer. It's more expensive than heart and kidney even. But to your point, yes, I would say in terms of total numbers, it goes heart, peripheral nervous, other parts of the brain. By the way, MELAS is a terrible disease of the brain from mitochondria. Lee's disease is a terrible brain from mitochondria. A lot of brain gets involved, not just the optic nerve. But what was not known until we showed it is that you also get optic nerve involvement in these other diseases. When a person is dying from Lee's disease at age 3, people don't bother measuring the vision, but the vision's gone, and the optic nerves get atrophic, and all this happens. So it's the canary in the coal mine, but bad enough other things get involved too.
Thank you for such an exciting talk, and I agree with you that aging and Alzheimer's disease also have similar pathology, and we see that in mitochondria playing a very important role in Alzheimer's disease in oxidative damage of lipids. Is it known what what molecules are damaged in the eye when disease occurs?
You mean the other diseases? Yes and no, of course. In Alzheimer's, for example, the damage tends to be the retinal ganglion cells again, but not in the a wave of degeneration. It occurs bit by bit. The damage does not involve the smallest fibers of the papillomacular bundle. It involves bigger fibers, first of all. So clearly, many of the rules that I made here for this mitochondrial disease don't apply in Alzheimer's. That said, I'll pick a better disease because it's better understood, and that's macular degeneration. Studies by Deb Farrington have shown that if you look at the cells in the middle of the scar for macular degeneration, everything's dead. If you look peripherally, you find out that those mitochondria have more mutations, deletions, than normal. And the closer you get to the edge of the lesion, the higher that number gets. So it is probably a regenerative phenomena by which the ROS causes more damage to the DNA, causes less efficient mitochondria, causes more ROS, and the gradient goes right from the macular degeneration out to the peripheral retina. So in that disease, I think we're talking about something pretty close to what we're saying here.
Yeah, I think they're very close also. The eye is enriched with docosahexaenoic acid and omega-3 fatty acid, and the brain is also enriched in that, and we find damage in the DHA in Alzheimer's disease.
When I was in medical school, there were two subjects that I found boring and didn't study enough: mitochondria and lipid metabolism. And now I say, those are the very two I should have been on top of.
I think we have time for one or two more
Here
questions.
I am with a question. Okay, first of all, you are fascinating and my favorite, and I am your biggest fan, as if you didn't know already. So my question for you, I have a few, is first of all, I'm really looking into the neuro side of our lives and how we learn and learning about ADHD and all the rest of it. I want to know how you're able to take in all this information and learn. How does your brain get you to learn things? That's number one, okay? Number two, when you are going to find a solution for us for Parkinson's, Alzheimer's, and all of that, and keep us young, when will that be for Deborah and me so we don't have to wait too long? Third question, very important, is who is going to play you in the movie and who is going to play Deborah? I need to know. So those are my questions. Please don't forget any of them.
Okay, so Bob, I don't really have to answer these questions, do I?
Yes, you do. You do.
Who's going to play Castro?
I want Kim Novak to play my wife.
Okay.
I can't. Oh, you know who would be good for me? Robin Williams. I'd have him play me.
Okay.
And to your last point, and I apologize for the self-aggrandizement here, they did write a book. It just got published.
I read it.
You read it, okay.
Yes, you gave it to me. Thank you. Thank
So,
you.
Anyway, there is the story out there, but nobody's been clamoring for screen time. In regards to the first question, I have on the top of my mind a conversation we had with the postdocs earlier today, which is people do things differently, of course, but the way my brain works is to assume that when my father was right, he always was right. When he once told me, I must have been 8 years old, and I was saying, this is stupid because I kept falling while the roller skates. This is useless information. Why do I need to know how to roller skate? And he said, there's nothing that you will learn that won't one day become useful to you. And I've been committed to that idea. So it's been more formalized by E.O. Wilson in his book called Consilience, where he says the deepest truths in every scientific field are the same. And the more you learn about one thing, the more you learn about all things. And finally, that the richest area to mine is not the middle of every field, but the edges of that field where it comes up against another field. One of the postdocs was talking about how he wants to use AI and look at the electrical changes in the heart. The most interesting part to look at right now is not the heart or AI, but the edges of those two fields, which will not only help new understandings, but will improve AI and improve cardiac physiology understanding. So my own feeling is that by scattering myself into a few slightly unrelated fields, I do better. But that may not be true for everybody.
Bob, may I ask a Zoom question?
A question from Dr. Bill Opel. Bill, we can hear you. Go
Hi,
ahead.
Alfredo. It's good to see you again after 37 years. Bill Opel here. I have a question about the microbiome. One of the things from our time-lapse films in the past is watching mitochondria very vigorously transit up and down neurofibers, and with the microbiome connected to the brain through the vagus nerve and all that. Do you have any reason to have any interest in microbiome effects on vision and on the oxidative events that are taking in the brain and those other events, and especially the nutritional elements and the things that are going on with transiting mitochondria?
Absolutely, and of course you make several of the points that maybe I should refer to here. Number one is, and forgive my pronunciation, I've been pronouncing it the microbiome. I'm regularly told by my colleagues like you that microbiome has more DNA than the DNA that we have on our own, that we consider us. And I say that's not true. The most DNA in your body is from the mitochondria. That beats out the microbiome. There's more mitochondria than there are bugs, germs. But there's more germ DNA than there is nuclear DNA. Number two, that the movement of mitochondria through an axon is a fascinating story for two reasons. Number one, the process of exoplasmic transport is ATP dependent, and yet the mitochondria are producing that ATP. It's sort of like having a train of donkeys that have to carry the corn on top of them. You can see how that's a setup for a reiterative problem. If they fall behind a little bit, they starve, and then they fall behind a lot. So I think exoplasmic transport of mitochondria is very interesting, especially insofar, and this is what's most interesting to me, mitochondria have to be made by the nucleus. They can't be made out in the axons or in the terminals, because even though the mitochondria carry their own DNA, that's only a small subset of the proteins that they need. I showed that complex 1. Of that complex 1, 3 of the proteins are made by mitochondria. The other 45 are made by the nucleus. So they have to be made in concert with each other as these assemblies are put together. And mitochondria don't live very long. They fall apart between 7 and 10 days. So if there is delays in this exoplasmic transport, the system will crash. And finally, maybe the third point, which I'm sure you'll find coherent with your own thoughts, which is that we tend to think of different systems as either being in competition with each other or at least totally independent. But in fact, 4 billion years of evolution has taught us that collaborations can work out best of all. We're learning that COVID doesn't want to kill us, it wants to live with us. The parasites want to evolve and change our immune systems to evolve so that everybody wins. And so it is that the microbiome isn't an infection from the outside meant to cause us problems, but something that has evolved with us and works with us.
Thank you.
Well, thank you very much, Dr. Sadun, for an absolutely wonderful lecture, and I want to thank all of our guests for attending this afternoon, and we hope you'll enjoy more of these in the future. Thank you so much.
Thank you, Bob. I've always been feeling so welcome when I come to HMRI. I consider this to be a very neighborly place for me.